Today we're going to start chapter 5, which is logarithmic, exponential, and other trans. Hey everybody, it's Mr. Grassi.
Hi, Mr. Grassi. How are y'all?
Good. Good. How are y'all?
Y'all's good? Wait.
What are you looking for?
I was trying to be as undisruptive as possible.
It's not going well.
No, it's not. If you have a winter break, extra credit.
Yeah, there is. So anyways, logarithmic, exponential, and transcendental functions. Today we're going to focus on logs, which is probably your favorite topic from pre-calculus, right?
No. Probably.
Yeah.
I hate logs. This would help me.
Hate is such a strong word. So in pre-calculus, you learned how to use the logs, you learned properties of logs, and you learned about this thing called the natural log, also known as ln, and you learned that there's a button on your calculator, and you could do all kinds. You learned that you could do all kinds of fun things with that natural log. Sorry. Today, however, we need calculus to explain where does that natural log come from, and it's kind of cool. Yeah, mathematical calculus sense. So today we're going to talk about the properties of the natural log function. We're going to talk about e, the number e, and we're going to find the derivative of a logarithmic function. So now we're going to go from derivatives to antiderivatives and now back to derivatives, and then we're going to go back to antiderivatives again. So we're all over the place. And then please just try to stay focused for 3 more days. So here we go. Natural log function.
Is this on the final?
No.
No. Solve that problem. Quick warm up here. When you get an answer, check with your neighbor, see what he or she got. What do you got? Some people have 0. Some people have does not exist. Some people have -1. Some people have 1. What is it?
Does not exist. All of those.
No, it can't be all of those.
It's a natural. E.
It is actually undefined. Why is it undefined though? Spacky, you said undefined, didn't you?
It's DNA, but same thing.
Okay, same thing.
Yeah.
Why?
Because when you take the integral of it, it would be like, the 1 over the 1 plus.
Right.
N, it would be 1 over 0. It's just
Good. So if we rewrite that as x to the negative first, the rule is raise the power by 1, that's okay. What's x to the 0? 1. That's not the issue. The issue is the number out in front, because the other part of the rule is multiply by the reciprocal of that new power, which means we're multiplying by 1 over 0, and that can't work. Okay? So that's an undefined integral. We can't solve it. But this complicates things. That red curve is the graph of 1 over x. How did we define an integral? Area under the curve. Is there area under that curve? Yeah, you can see from 1 to 4, there is area there. Therefore, how can that be undefined? Shouldn't that be a numerical value?
Yeah, it should.
It should. But we can't find it using that integral, which is what that paragraph says. Okay? It gives us a a dichotomy there that doesn't work out. The graphical approach says there's got to be a numerical value there. The calculus says you can't do it, you can't solve that problem. This explanation is actually the definition of what a natural log is. Okay. So a natural log, aside from writing down that formula, you want to think of it this way. A natural log is defined as the area under the curve of 1 over x from 1 to whatever you're looking for the natural log of. So let's suppose I'm looking for the natural log of 2. I know you're writing, but I'm going to click back one. The natural log of 2 would be the area from 1 over to 2, that little region under there. Okay? That's where natural log comes from. So like I said, last year you worked with it, you calculated with it, you talked about properties, you've done all kinds of cool things with it, but this is where in calculus we get the official definition of where that function comes from. Notice that little tidbit there too that says x has to be greater than 0. You can't take the natural log of a negative number. And last year in pre-calc, you probably looked at the natural log function. It looks like that. So it's asymptotic to the y-axis. Its domain is 0 to infinity. Its range is negative infinity to infinity. It's continuous. It's 1 to 1. It's concave down. It's always increasing. It's a fun little function. And notice there's no value to the left of the y-axis, which explains why you can't take the natural log of a negative number, because there's nothing there. Okay, so going back to pre-calc stuff, reviewing the properties of logs. Let's start by talking about number 1. Why is the natural log of 1 equal to 0? Other than the fact that it's a property. Explain to me, now that you're in calculus, explain to me why the natural log of 1 is equal to 0, Shannon.
Isn't it because it's going from 1 to 1, and if it's the same number, it's 0?
Perfect. Did everybody hear her?
Yeah.
If you take the integral from 1 to 1, regardless of what the function is, if you go from a number to itself, you're always going to get 0. Well done. 2, 3, and 4 are just log properties that you did last year. The log of a product is the sum of the logs. The log of a product is the sum of the individual logs. So in other words, you can turn the log of a multiplication problem into an addition problem. Exponent power. If you're taking the log of something raised to a power, you can bring that out in front. And then the last one is the quotient. The log of a quotient is the difference of the logs. Multiplication becomes addition, division becomes subtraction. One other thing that comes up frequently is the difference between these two things. What's the difference between those two?
The second one is.
Matt?
The first one, you take the natural log of x and then take that to the third power, and the other one is different. It's like number 3.
Correct. This is the same as number 3. I can rewrite this as 3 times the natural log of x. I can't do that for this one. Okay? So this property for number 3 applies to the second one there, not the first one. Beautiful. Okay. So just a quick review again. If you want to take the natural log of a fraction, you can split it into a subtraction problem. If you want to take the natural log of a square root is the same thing as an exponent problem. You're raising it to a certain power. So you can bring the exponent out in front and get something like that. And then this one we can break up 2 times. First of all, it's a division problem, so you can break it into a subtraction problem. And then the first one is a product, which can be broken into a sum, and so you get something like that. In pre-calc last year, you worked with logs going in both directions. You took a complicated log and broke it into parts, but then sometimes you also took the parts and went backwards. We don't frequently go backwards in here. We're just concerned about breaking it up versus putting it back together. So that should all be review, yes? Beautiful. Okay, now let's talk about E. Who has a $20 bill I can borrow? Thank you, Alex. I'll give it back. This is a cute little nerdy math thing to remember the number E. Everybody know the number E, by the way?
2.7 Jackson.
2.7 Jackson. Okay, so this is a $20 bill. Okay, that's a $20 bill also. Who's on the $20 bill? Jackson. Do you know what president he was?
7.
He was the 7th. Do you know what year he was elected? 1828, and he ran for 2 terms, right? So it's a $20 bill. He's the 7th president of the United States. He was elected in 1828. He ran for 2 terms. I know that's cheating, just go with it. And then if we do a little bit of origami here, we can fold the $20 bill up into,
Oh, that's a 2 point?
yeah, it's a 20. If I fold the $20 bill up into this shape, I get,
A triangle.
what kind of triangle, Abby?
Right.
30, 60, 90.
Not a 30, 60, 90.
45, 45.
45, 45, 90, also known as a 45, 90, 45. So there's E to 3, 6, 9, 12, 15 decimal places.
Wait, what's the 71?
It's not. It's a 7. 7th President of the United States. Elected in 1828, ran for 2 terms, 1828. 45, 45, 90 triangle. You probably won't need to know E to, what did I say, 15 places, but it's an interesting way to remember it. Now, where does E come from? Anybody know?
Shows up in nature. It shows up, yeah.
It what?
Shows up in nature a lot.
How so? Well, you guys jinxed. You owe each other a Coke. It's cute.
They're both in Mr. Bride as well.
Oh, where does it show up in nature?
In like symmetric shapes on plants and stuff.
Symmetric shapes on plants.
Symmetric forms on plants. That's where it can show. Bacteria reproduction.
Bacteria reproduction. How so?
Well, I don't know, just a lot of the functions that have.
It sounded impressive.
Yeah.
That's like the exponent by which they divide or something.
Yeah, that's an exponent.
Yeah.
I actually don't know.
I
Oh,
don't
yeah,
either. I just
chemistry.
don't
Chemistry
see
shows
it.
up too.
It's used
We
as like a
can tell you what it is when you
population
believe it.
equation.
Yeah.
So that would make 40 bacteria. He was very
I just remember problems involving bacteria. It does.
Yeah.
Any particular reason you got to think for bacteria?
I don't know, I don't know. Last
That's
year
like
I
the K
solved like
value
so
or
many of
something.
those.
It's what? I'm
It's
sorry?
like the K value or something like that for like bacteria division something. Yeah.
Cool. I didn't know that.
Something like that.
I can show you where it comes from mathematically. Let's go back to this graph that we talked about already, the 1 over x. See this pink region under the curve? I want that pink region to have an area of 1, like it says here. In order to get a pink region being equal to an area of 1, I have to come over to the value of E. The 2.7, 12A, 128, et cetera, okay? That's where E comes from. It's the area under the curve. So I got it in the next slide, so there it is. Okay, so the natural log of E is the area under the curve from 1 to E that guarantees that that area under the curve is exactly 1. Somebody asked 4th hour if it's a repeating number or if it, I don't know anything about how far it goes out. I don't think it's like pi. I think it does terminate or repeat at some point, but it's a pretty exact number. Okay. Which gets us this little guy down at the bottom. The natural log of E is equal to 1. Remember from pre-calc last year that the natural log is the same thing as log base E. So you did logs with log base 2, log base 10, log base 4, that kind of stuff. Natural log is log base E. Okay, so get out your calculators. Let's make sure you can do this on your calculator, but we also want to talk about the calculus involved. So if I give you this first problem, check to make sure that on your calculator, when you take the natural log of 2, you get 0.693. I don't know why you wouldn't. It doesn't matter what setting you're in. The more important question is, where does that number 0.693 come from, and or what does it mean? Alex, give it a shot.
Area of 1 over x from 1 to 2.
Perfect. Okay, the natural log of 2 is the area under the curve of 1 over x from 1 to 2. So if we go back to this picture on the previous slide, this one, from 1 to 2, it would be the area of that little region there. Okay. If you go further out to 2.7, blah, 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 then you get 1, but for this one, you only get 0.693. And notice that if we jump up to the log of 32, the number gets bigger. The number should continue to get bigger because the area will get bigger. But it's going to get bigger slower. Why?
Because
John?
there's a horizontal asymptote at 0.
Correct. It's getting closer and closer to the x-axis as you go further out. So what's the limit of 1 over x as x approaches infinity? 0. Yeah, throw a little bit of limits in there. Then, if you take the natural log of 0.1, you get a negative number. Why? Mitch?
Because it's the antiderivative from 1 to 0.1, and 0.1 is smaller than 1.
Good. So why is it negative?
So
How do you resolve that problem when the b term, when the b limit of integration is smaller than the a term?
you would switch them and put a negative sign in front.
Perfect. Good. All of these are positive numbers. You can only take the natural log of positive numbers. However, you can get negative answers. And the negative answers would be anything between 0 and 1. Because again, as he said, we're having a limit of integration on top, which is smaller, so you have to flip it and stick a minus sign in front of it. Okay? Okay, derivatives. People make this more difficult than it needs to be. It's really easy if you remember the buzz phrase I'm going to give you. So whenever you have to take the derivative of a natural log, you're going to burn this idea into your brain, and it's going to be pretty simple. It's this. We don't care about 1. In fact, don't even look at 1. Don't look over there. Just look at 2. If I want to take the natural log of anything, all I have to do is take the derivative of that anything and put it over itself. That's it. U prime over u. Whenever you see the natural log, the derivative of a natural log, you're going to think u prime over u. Okay, so again, don't make it more complicated than it needs to be. So if we do this, what is the derivative of the natural log of 2x?
2 over 2 over x. Or no, 1 over x.
I'm sorry, you said 3 things there. Which one are we going with?
1 over
Why,
x.
Adam?
Because you take the derivative of 2x and it's 2, and then it goes over 2x.
And then
Simplify.
you simplify. Perfect. Everybody hear that? Derivative of 2x is 2 over 2x. 2 over 2x simplifies into 1 over x. And you stop there. Okay, so u prime over u, 2 over 2x, which equals 1 over x. Okay. How about this one? What's the derivative of the natural log of the quantity x squared plus 1? Allie, you look like you're wearing a toga. Jackie, what do you got?
2x over x squared plus 1.
Perfect. Okay, which can't be simplified, so we stop there. There it is. Okay. How can we make it more complicated?
Trig.
I didn't think of that. We could make it more. I didn't use trig. Sorry, I dropped the ball. I did this instead. I made a product rule. It's been a while since we've done product rule. So just as a refresher, I'm taking the derivative of x times the natural log of x. This is a product rule involving logs. We can also look at a log involving product rules. We'll get to that later. We're going to crawl before we run here. So refreshing your memory on the product rule, the first times the derivative of the second plus the second times the derivative of the first, which I wrote all that out here. What's the derivative of x? 1. What's a derivative of x is 1. What's the derivative of natural log of x? 1 over x. Okay, so this becomes that. Derivative of natural log of x, u prime over u, x is, the derivative of x is 1, 1 over x, and the derivative of x is 1. Mitch?
Could you also use the one rule from the previous slide and make it x to the x?
Ah, perfect. You could, well, you could do it a couple different ways. Do you know how to take the derivative of x to the x?
You should teach us.
Good point.
I will. That's coming up in this chapter. That's one way to solve. There's actually 3 ways you can solve this. That's one way. You could turn it back into a exponent problem if you knew how to take the derivative of x to the x. You could also, no, I couldn't do that. Never mind. 2 ways to do it. Your way and this way. I was thinking it was a natural log and we could use natural log properties to split it into an addition, but that would be the natural log of a product, which again we'll get to later. Okay. And then this is what we talked about. What's being raised to the third power here? X or the natural log of x? Natural log of x. So when you take the derivative of something raised to the third power, you bring the power in front, reduce it by 1, chain on the derivative of the thing inside. And again, the derivative of natural log of x is just 1 over x. Kirsten?
1 plus the natural log of x, isn't it supposed to be over the...
No, because it's a product rule. I split it into different parts. That whole u prime over u happens here, and that's the only place it happens.
Okay.
Yeah, because the product rule splits it into 2 separate terms. Okay, so again, don't make it a difficult idea. It's just u prime over u over and over and over again. It can get fairly complicated, but it's still, at the grassroots part of it, is just u prime over u. Okay, so, let's not go there.
Go back for a second.
Yeah. Let's stop for today, because you're not ready for logarithmic differentiation. Let's let this sink in for a little bit. We'll come back to logarithmic differentiation tomorrow. It's a new way to take the derivative of complicated problems using logs and the u prime over u idea. We good?